Hi everyone, so welcome to the chapter of Hydrogen's JEE and NEET session. For today we will be observing 25 important questions. Okay, and there will be several questions wherein you will see that there is just not one, rather there will be two correct answers. So let's get started. Question: which of the following statement about hydrogen is incorrect? Alright. So they are asking about which of the following statement is incorrect, not correct answer. Okay, hydronium ion, that is H3O plus, exists freely in solution. Actually, this is correct. Okay, let's see option 2, that is the dihydrogen does not act as a good reducing agent. Actually, dihydrogen acts as a very good reducing agent. Okay, so therefore we are doubtful about this particular option here, that is B. Okay, it is helpful in reducing things, that is displacing oxygen from oxides. So therefore B is one of the correct answers. Let's not jump into conclusions, we'll observe all different options. So option C says that hydrogen has 3 isotopes, correct, of which tritium is most common. Now when they are speaking with respect to tritium, actually it's a very rare form of hydrogen. Also it is a radioactive in nature, so therefore we cannot expect that particular thing to be correct. So we would say that even B and C over here options are incorrect. Let's check option D. Hydrogen never acts as a cation in ionic salt. Again, actually this is also correct. Okay, it does not act as a cation, that means H plus type of species. So therefore, here we have two options which are correct, that is B as well as C. Now, you would face such kind of questions, wherein if you select only B, okay, so you will be awarded partial marks for this. Now, if I am going to select A and B, one correct option and one wrong answer, over here I am going to lose complete marks. So you should be observant, you should observe the things very carefully while selecting the things. So here, for this particular first question, the answer is option B as well as the option C. Let's go with the next question. Question number 2. Some statement of heavy water are given. Heavy water is used as a moderator in nuclear reactor. Yes, one of the correct answers. Heavy water is associated more than the ordinary water, again correct. Heavy water is more effective solvent than ordinary water. Now here option C is not a correct one because of the heaviness of heavy water, okay, especially because of the heaviness of deuterium. In this particular case, what happens is it lowers down the rate of reaction, it slows the reaction process. So therefore, in such condition, heavy water is not an effective solvent. Let's observe the options given. Okay, so options A and option B should be the correct answer. Let's observe. A says that A and that is option 1 and 2 is correct. B says that 1, 2 and 3, of course it's not correct. C, 2 and 3, not at all. D, 1 and 3, again not correct. So therefore, our answer lies with, that is A, 1 and 2, option 1 and 2. Coming forward with the question number 3, one of the most important questions. So, which of the following pair of substances on reaction will not evolve? They are saying that it is not going to evolve hydrogen gas. So here, if we observe, it all goes with the electrochemical series. Okay, so when we take a look with respect to iron and steam, they are going to react. They are going to react in order to give oxide of iron along with elimination of hydrogen gas. Okay, same is over here. This particular reaction gives sulfate along with elimination of hydrogen gas. Whereas sodium and ethyl alcohol, when we observe this, okay, so if I am going to take a reaction between these two, C2H5OH. When this reaction occurs, it gives me a major product as NaOC2H5 sodium ethoxide. Okay, Now, along with this, there is an elimination of hydrogen. Of course, it is not balanced. In order to balance this entire thing, let's take over here 2, here 2. Therefore, 2 NaO C2H5. What happens is we have 2 hydrogens. This particular thing is eliminated in the form of hydrogen molecule. Now, here, if we observe this particular case, okay, here, because of the electrochemical series, copper lies below hydrogen in the electrochemical series, due to which this reaction is not possible to evolve hydrogen. So therefore, this is the answer, which is not going to give us any hydrogen. So, moving towards the next question, what we have here is which of the following group of ion makes the water hard? Now, hardness of water is because of the bicarbonates of calcium and magnesium, as well as because of the calcium and magnesium's association with the chlorides and sulfides. So, what we have to remember here is about the calcium and magnesium salt. Okay, and if this particular thing is combining with HCO3, that is a bicarbonate, then it is going to form a temporary hard water. Okay, while on the other case, if this particular thing, that is the calcium as well as magnesium, are going to combine with either chlorides or sulfide. Okay, sulfates. So in such cases, it is going to give us a permanent hard water. Now, let's see here. Sodium and bicarbonates, that is the sodium bicarbonate, NaHCO3. Okay, so in that particular case, whatever water we get is not going to be hard water, it is going to be soft water because of the sodium ions. Okay, so option A is not correct. Magnesium and chloride, yes, because of these particular ions, water will become hard water. Therefore, option B is correct answer. Let's go to C. Potassium and sulfate. Again, potassium salts will not make the water hard. Okay, ammonium and chloride. No, again, ammonium chloride will not make the water hard over here. Okay, so therefore, the option B is the particular only one option which is going to make the water hard. So, one would expect the proton to have very large. Now, what is a proton? A proton, over here, if you see, is nothing more than H plus ion, right? So, a proton actually has a smaller radius. Okay, a hydration energy is very quite high in this particular case. Ionization potential, no, it has already lost an electron, so we cannot expect the ionization potential here. Charge remains for the +1. Okay, so +1 is a smaller charge. Ionization potential we cannot expect because it has already lost an electron. Hydration energy seems to be a correct answer because the radius is also smaller enough for any cation when we compare to that of the parent atoms. Okay, so therefore, in this particular case, it is the hydration energy. Coming towards the next one, the ionization of hydrogen atom would give rise to. Alright, so if we have a particular hydrogen atom in its gaseous state, okay, so as we supply energy to this particular hydrogen atom, as we go on supplying the energy, what will happen is that particular electron absorbs an amount of energy and it gets excited. It leaves the entire atom outside. Correct? It leaves the atom and it goes outside, leaving behind the hydrogen with a positive charge. And this particular positive charge ion is nothing more than a proton, and this one, that is a proton, is the answer here. Okay, so the ionization of hydrogen atom would give rise to a proton over here. Okay, so moving towards the next question. Coming towards the next question, and that's question number 7. Which of the following metals evolve hydrogen on reacting with cold dilute nitric acid? So here, if we observe, if you want to eliminate hydrogen gas, okay, one of the preliminary things is hydrogen is eliminated in the form of H2 right? But if we observe, magnesium is one of those particular species or one of those particular elements given to us right now, which is capable of existing in Mg+2 state. While on reacting with dilute nitric acid, Al becomes as Al+3, as well as Fe becomes as Fe+3. Okay, over here these two are not going to give us, all these three are not going to give us any particular hydrogen gas on reaction with dilute nitric acid. Only one thing that gives us is magnesium. Let's see with respect to an example. Okay, magnesium on reacting with dilute HNO3, okay, it will form Mg NO3 twice plus hydrogen gas is going to get eliminated. Okay, now how do we come across this particular conclusion is, if you observe, magnesium exists in oxidation state of +2, while HNO3 again exists in oxidation state of -1 when it is for NO3. Okay, so now what happens is, if we just cross multiply this without taking into consideration of the charges, let's just take into consideration of the magnitude. So when we take into consideration of magnitude, Mg becomes as here Mg, while NO3 is going to be 2s. So this is how we get the formula for the salt. Okay, so along with this, of course, there is an elimination of hydrogen gas. So it is the magnesium which has a capacity to evolve hydrogen, not copper, neither aluminium, neither ferrous. Moving forward with the next question, and that is question number 8. Hydrogen will not reduce. It is going to reduce cupric oxide because of, again, electrochemical series. It will reduce cupric oxide. Reduction means what? It is going to displace oxygen. Okay, heated cupric oxide, yes. Heated ferric oxide, also yes. Heated stearic oxide, yes. But only one thing that we have to remember is hydrogen will not reduce heated aluminium oxide. Okay, so it is not going to react over here, aluminium oxide. So we cannot expect the reaction with aluminium oxide. So therefore, it is not going to react with D. So coming towards the next question, and that is question number 9. The sum of the number of neutrons and protons in the isotope of hydrogen is. So, the number of neutrons, alright, so observe the isotope of hydrogen. So, isotope of hydrogen, what we know is the protium, okay, next one is the deuterium, and next one is the tritium. We have 3 of them. Okay, so they are asking us the sum of number of neutrons and protons. Alright, so neutrons, protons. So neutrons, the number of neutrons in hydrogen, 0, right? So there is 0. In deuterium, there is a presence of 1 neutron, and therefore it becomes a bit heavier. The number of neutrons in tritium are 2. Okay. While when we observe, the number of protons remain same. That is 1, 1, and 1. So sum over here remains as 1, here it remains as 2, here it remains as 3. Okay, so therefore we have only one option there, and that is the D. So the sum of number of neutrons and proton in the isotope of hydrogen, and there is only one possibility, and that is for tritium. So this is the answer over here. Right? So answer for this particular case is the D1. Okay. Moving towards the question number 10. The oxidation state state exhibited by hydrogen in its various compounds are. Alright. Now, first try to understand this simple fact. Whenever we have hydrogen and this hydrogen is connected to, let's say, metal. Now, metal over here is an electron donor. That means it gives the electron to something that has been attached to it. In such cases, what will happen is the electrons move towards the hydrogen, thereby which this particular hydrogen will develop -1 charge. Okay, similar is the case when hydrogen is attached to more electronegative elements such as halogens, wherein the halogens are prone to drag those particular electrons towards themselves. As they drag the electrons towards themselves, what will happen is this particular halogen develops negative charge, while this fellow loses its electron towards the halogen, so therefore +1 in this particular case. While we have two different scenarios here, wherein the hydrogen is connected to metal, wherein the hydrogen takes electron. In such cases, +1. So in such cases, it is -1. While in particular case wherein the hydrogen loses electron, it becomes as +1. There are cases such as a simple molecule of hydrogen, wherein the electrons remain exactly in the center. It has been shared by both of them. In this particular case, oxidation state of this hydrogen remains as 0. So we have three options over here: -1, 0, +1 state. So A, -1 is in the metals connected to hydrogen, metal hydrides. B, 0 is for this fellow over here in the center. And and here is a +1 for this. And we will say that it is going to exhibit all the three oxidation states, and that is the +1, -1, and 0. So, correct towards the question number 11. When zeolite, which is hydrated sodium aluminum silicate, is treated with hard water, okay, the sodium ions are exchanged with. Okay, so if you do remember, we had represented zeolites as NaZ. Okay, sodium aluminum silicate. So wherein Z would represent to us the aluminum silicate section of it. Correct? Now, when we take this particular thing and when we insert this one into the water, and the water is of course an hard water, what happens there is in the hard water we have different particular ions, especially that of the calcium and magnesium. Now, when these particular things are exchanged with the sodium, so therefore when we dissolve sodium, aluminum silicate, it forms as Na plus Z minus, right? So Z minus is going to be combined with these, okay, forming CaZ2, that is 2 times. Okay, so therefore this is what is eliminated into the water, making the water soft. So therefore we can say that sodium ions are exchanged with ions of calcium as well as with magnesium. So therefore, let's check here. So H plus ion, no, it is not going to exchange that. Of course, what we have the next option, and that is going to be B, that is the calcium plus 2 ions. While OH minus ions and SO3 minus 2 ions are exchanged in an ion exchange methods, right? That is a synthetic ion exchange. Coming towards the question number 12. Match the list 1 with the list 2 and select the correct answer using the codes given below. So, list 1, that is heavy water. Okay. Now, we have to first match this particular list with list 2. Okay. Let's say heavy water is 1, 2, 3, 4. Heavy water is 1, temporary hard water is 2, soft water is 3. Permanent hard water is 4. Now, if you observe heavy water is nothing more than C, that is D2O. So I will say that 1C. Temporary hard water is formed because of the bicarbonates. It can be of the calcium, it can be of magnesium. Not a problem. In this particular case, they have given us magnesium. So 2, I would say it as A. 3, soft water because of there are no ions. So therefore 3 goes with C. Sorry, C goes with B over here. Final thing, what remains is the permanent hard water. Permanent hard waters are especially due to the sulfates and chlorides of calcium and magnesium. So therefore, 4 goes to D. So therefore, let's write over here 4 is D. Let's see if we can match any of these. So 1C, 2A, 1C, 2A, okay, 3B, 3B, 4D. So therefore, the option in this particular case is going to be the D. Let's go with the next one. And that is question number 30. Semi-water gas is a mixture of. Okay. So first thing is about the water gas. The water gas is nothing more than a mixture of hydrogen gas plus CO, carbon monoxide. Okay, but the semi-water gas is a mixture of the 3 constituent gases, and those are hydrogen plus carbon monoxide plus nitrogen. Okay, so these are the gases which are going to give us a combination for a semi-water gas. So let's check. Oh, here SO plus H2O, CO plus N2, yes, that is the C, CO carbon monoxide plus H2 hydrogen gas plus N2, that is a nitrogen gas, which forms the composition of a semi-water gas, right? So let's go for the next one. Going forward with the question number 14, which of the hydrides are called as allanite? So allanite is actually the name for lithium, aluminium, hydride. Okay, so lithium aluminum hydride is also known as allanite. So this is the important name for one of the hydrides, and that is called as the lithium aluminum. The maximum number, the next question, maximum number of the hydrogen bonds a water molecule can form. Now this is a little bit like a logical form of question. Okay, so in this particular case, what will happen is we need to understand the structure first. Let's consider oxygen connected to hydrogen over here and the next hydrogen over here. It has of course the lone pair of electrons, one over here, another one over here. Right? Now, the adjacent molecule with respect to this, let's say there is another oxygen over here connected to 2 hydrogens. So what is going to happen is these lone pair of electrons will attract the hydrogen. Right? Similar is the case when we have the other adjacent molecule of water here. These are the hydrogen bonds, right? Similar is the case about this oxygen. It forms hydrogen bond with the adjacent water molecules. So, if I take into consideration of one water molecule, and that is this. So here, the number of hydrogen bonds that one water molecule is going to form is 1, 2, 3, 4. So total number of hydrogen bonds that are formed are 4. Okay, so we need to observe things carefully before answering them. So here the maximum number of hydrogen bonds a water molecule can form are 4. Question number 16 says that the hydride gas refers to inability of. Now, hydride gap over here, if you observe, hydride gap, okay, that means these are the elements which are not going to give us the hydrides on reaction with hydrogen. These elements will not react. Okay, so noble gases to form the hydrides, that is the inability of the noble gases to form hydrides, it's not named upon that. It's actually in the transition series. In the transition series, that is the group 7, 8, 9 of the D block in order to form hydrides. Okay, these are the actual elements. When we take a look into the entire periodic table, the elements of group number 7, 8 and 9. Okay, these particular elements cannot react with hydrogen in order to form the hydrides. Such particular entire group, we call it as the hydride gap. It's actually a hydride gap. Okay, it should be an hydride gap. So, we'll proceed to the next. Coming towards the question number 17, which pair does not show hydrogen isotopes? Okay, now observe here, protium and deuterium, these are the isotope of hydrogen. So therefore we have protium, we have deuterium, we have tritium. These are isotopes of hydrogen. Correct? So even deuterium and tritium and protium, B, C and D, all these are isotopes of hydrogen. While when we take a look into the ortho and parahydrogen, okay, these are the allotropes of hydrogen, wherein it differs by the spin of that particular proton. Correct? We have an ortho spin, we have the para spin. Okay. Now, question number 18 is also in relation with the question number 17. So what it says, ortho and parahydrogens are going to differ in. Okay, so when we were taking a look into the ortho and parahydrogens, let's say these are the molecules of hydrogen. So what was happening here is depending upon the spin of nucleus. Okay, and when we see the spin of the nucleus, especially in the spin of the nucleus, it is the proton spin. Okay, so how is this particular proton is spinning? Whether it is spinning along the clockwise or whether it is spinning along the anti-clockwise. Okay, so here, if both the spins are in a same direction, the spins of proton. Okay, so proton spins. If the proton spin are in a same direction, we call them as the ortho. While if the particular proton spins are in different directions, we call them as para spins, or we call it as the parahydrogens. So, ortho and parahydrogens differ in the spin of its protons. Okay, so it is actually in the nucleus, it's about the proton spins. So, option is coming towards the question number 19. Which of the following explanation is the best for not placing the hydrogen with the alkali metal or halogens? Okay, now the ionization energy of hydrogen is higher for the group of the alkali metals or halogens. Okay, if we go through the properties, you will see that about the ionization energy, and it is almost equivalent to that of the halogens, especially in the halogens, it's with respect to chloride. Okay, B, hydrogen can form compounds. Of course, the compounds can be given by the halogens as well as by the alkali metals. Okay, so option C, hydrogen is much lighter element than alkali or halogen. Option D, hydrogen does not contain any neutron. Okay, option D is not a correct one. Okay, it has nothing to do with the neutron actually. It's about the weight. So, hydrogen is much more lighter element to be placed with the alkalis or with the halogens. Okay, so therefore, we have the hydrogen is much lighter when compared to that of the alkalis and the halogens. So, therefore, they are not going to place this hydrogen despite of its similarities with the alkali and with the halogens. We place it separately. Towards the question number 20. the difference between the neutron and proton is positive form. Now we had already seen a similar kind of question with respect to the isotope of hydrogens. Okay, so here the difference between the neutrons and proton is positive form. Alright, so let's take over here protium, let's take here deuterium followed by tritium. The number of protons and the number of neutrons. In all the cases we have one proton. But the number of neutron in simple protium or the simple hydrogen is 0, while that of the deuterium is 1 and the tritium is, of course, that is 2. Correct? So the difference between the neutrons and protons, so is going to be for difference is positive for, so here it is going to give us 0, here it is going to be minus 1 and here it is going to be 1. So therefore, it's the answer that is going to be a tritium atom. Number 21. The conversion of atomic hydrogen into ordinary hydrogen. Okay, they are speaking about the reaction between the two atomic hydrogen in its gaseous form. Okay, now in order to form hydrogen molecule. Now, this particular case, when we take a look at this particular case, atomic hydrogens are much more reactive, they are much more unstable. Okay, due to which these particular things react. Okay, they react and in order to give us a stable molecule, and if something wants to become stable, it has to release a lot of energy. Okay, so therefore, whenever the unstable atomic forms of hydrogen react, in order to give us the hydrogen molecule, a lot of energy is evolved. Such kind of reaction which gives away energy, we call them as exothermic reactions, or in this particular case, we are calling it as an exothermic change. So therefore, question number 21 gives with the answer as A, and that is going to be the exothermic reactions or exothermic change. Okay, while a particular reaction which absorbs the energy, okay, it is not going to liberate, rather it is going to absorb the heat energy, temperature lowers down. In such kind of conditions, we call them as the endothermic changes or endothermic reactions. Question number 22. The approximate mass of tritium oxide. Now tritium oxide, that is nothing more than T2O. Okay, oxygen mass of oxygen, what we have is 16 AMU, right? While tritium is an isotope of hydrogen with mass of 3 AMU. Why it is 3 AMU is because of the contents of the 2 neutrons and 1 proton. Okay, when we combine, of course it's 3, but of course we have 2 tritiums here, so therefore let's say that there are 2 tritiums, so therefore 16 plus 3 plus 3, you will get that 22 AMU. Right? So answer is 22 AMU. Towards the question number 23. Hydrogen resembles halogen in many respects, for which several factors are responsible, of which the following factor is most important in this respect. That means there are many factors which are going to help us in order for the resembling the hydrogen with the halogens. Okay, but there is only one particular such kind of reaction or such kind of property which will show an immediate relation between the hydrogens and the halogens. Okay, so therefore, if we observe its tendency to lose an electron in order to form a cation, hydrogen can easily donate or easily lose an electron, but it's not the same character with respect to halogen. Halogens cannot easily lose electrons. Okay, so A is not correct. Second one, its tendency to gain an electron in its valence shell to attain stable electronic configuration. Yes. Here, if we observe, it accepts the electron, then the electron goes into the outermost shell, which will represent to us electronic configuration of helium. Okay, so as the same is the case when we observe the halogens. Halogens accept Okay, any halogens are there, they accept the electron in order to form electronic configuration, and this electronic configuration is going to be similar to that of the different noble gases. Okay, so here is the thing wherein the hydrogen resembles or exhibits similar property to that of the halogen with respect to acceptances of electron. Coming towards the next question, and that is question number 24. Why does H plus ion always gets associated with the other atoms or molecule? Okay, so they are asking that why H plus gets associated, why it goes and joins with the other complexes easily. Okay, so A option is ionization enthalpy of hydrogen resembles to that of alkali metals. It has nothing to do over here. No. Ionization enthalpy of hydrogen. No. Okay, it is not the perfect answer for this particular question. Ionization enthalpy means you are just removing an electron and you are trying to compare that particular property with that of the alkalis, which is not a correct answer. Its reactivity is similar to that of the halogens. Again, it's not a correct answer over here. It resembles to both alkali and halogens. Of course, it's not again a correct answer. So in option 1, they are saying that it is resembling alkali. In option 2, they are saying that it is resembling to halogen. In option C, they are saying that it is resembling to both alkalis as well as the halogens. Okay, so therefore, all these three options are not correct. But when we observe option number 4, it is going to lose an electron in order to form from the hydrogen, which will give us a proton. Okay, and this proton actually has a very smaller size when we compare to that of the actual atom of the hydrogen. Due to which results in the smaller size as compared to that of the other atoms or ions, due to which it becomes highly unstable, and is not going to exist freely, due to which in order to exist it combines very easily. Okay, so protons readily combines in order to form stable molecules. It needs stability, and therefore option B is the correct answer. The last question for this particular session, and that is which of the following hydrides is an electron precise hydride? Okay, so in the hydrides, if we observe, we have different classes. One is the electron rich, electron deficient, electron precise, depending upon the number of electrons that are available in order for drawing the Lewis structure. Correct? So actually, if you observe the first one, that is B2H6, this one falls under the category of the electron deficient. Okay, it falls under the category of the electron deficient hydrides. While NH3, it has a low pair of electron on the nitrogen, and therefore it falls under the electron rich hydrides. Of course, even the H2O falls under the same category of the electron rich hydride. Final one, what we have is CH4. CH4 is only one hydride what we have, which will show us the exact required number of electrons for representing a Lewis structure. Okay, these are the structures which are called as Lewis structure. The number of electrons are safe sufficient precisely for what we require for drawing that particular structure, and therefore option is D1 here. Right? So this is it for now. 25 questions.